wonder if she can hear us. She can. It's not good.
Well, I hope she can hear us. We're gonna find out though. Okay, folks. So we're very close to the end. We talked already about stellar graveyards. I'll update these a little bit more. We're gonna get into what we call galaxies. Focus, please. Galaxies. And we'll talk about the foundations of cosmology and what it means when people say the word Big Bang. And then we'll be done. We may or may not have time for aliens. Right here is what I call bonus lecture. So we can vote on what bonus lecture we'll do. And a lot of people like aliens, obviously. Okay. And one thing that we're going to do on Monday is that we'll probably have the observatory. But someone showed me today that there are thunderstorms predicted. So if that does end up being thunderstorms, then we'll do galaxy classifications. It's less fun because you don't get to see the moon. But we will have an opportunity to see the moon on the 10th, 70%. So we'll be able to finish both of those. And I will print out both the deep sky and the moon labs. So if you have your pictures from that time period or you remember what you saw, you can fill those in.
So I kind of did the moon lab with my own telescope. Is that okay? Or do you not want?
How would you do the moon lab with your own telescope?
Like I had a telescope. It was the day we.
And you can
supposed to do the moon lab.
You can switch eyepieces.
Yeah.
Oh, okay. Yeah. Sure. Yeah.
Is that one that was like super zoomed in? That was like,
yeah. Terminator, yeah.
Terminator.
Yeah. Perfect. Yeah. I mean, the idea is get you to look at the sky. So if you're looking at the sky, you get credit for looking at the sky. Okay. I think lab is pro. I think meteorological weather forecasts for 6 days from now are bad, but we'll see. 5 days from now. Okay. Any other questions? It is. Well, time keeps on slipping. Yeah, where does it go? Into the future. Okay. Let's get started here. We will survive that. Why don't we turn some of the lights off? Because it's the more fun part. It is beautiful, right? So the problem with galaxies, they are gorgeous.
What?
They're just boring. No, not all. I like that. I know they're gonna fall asleep.
She's had a lot of coffee today. I don't think you'll want anytime soon.
Okay, what are we looking at?
Galaxies.
Good. And this is gonna be just one of those like, what do you see type moments? Right in the middle. There. We're in the middle of the image here.
Nice.
There's some cluster pictures.
Okay, you see like bright areas like here. Okay, anything else?
Some dark areas.
Dark areas. You see like dark here.
Yeah.
Good. Anything else? Blue. Good. Yeah. Blue and red. We like to use our color names. Where's the green stars?
I see one.
Where? There's no green stars.
Oh, it's like what?
It looks like it. It's like it looks like us.
Dog's full. There are no green stars. Okay, what else do you see? Anything else?
See some yellow.
You see some yellow, yeah. There's definitely a lot of yellow here, right?
No, like a little bit to the right. Yeah, right there.
Here in this region?
Yeah.
It's like reds and yellows, good. So there's definitely some nice colors in here. Anything else? Circular? Yeah, it's got like a swirly pattern to it, right? Okay, that's important. Anything else? What's that? No, you don't see aliens.
She's
beautiful. Beautiful. Okay. All right. So I also see something here where I see like a band this way. And if I let my mind connect the picture, it kind of comes over here. Whereas this piece connects sort of backwards that way. I'm noticing only two major bands here. And we'll see if that's the case later on. Okay. Okay, so they call this thing the Milky Way galaxy. And it appears as a faint band of light over our heads. If there were no light pollution, we lived in even just pre-industrial times, so 400, 500 years ago, you would see this every night.
Are there parts of the world right now where we could see that?
Yeah. You can go to Mojave, you can go to Death Valley. That's not hard to do. But most people used to be able to look up and see millions of stars every night. Now you see hundreds or thousands, depending on where you live. So there are concerted efforts to attempt to fix the dark sky problem, because in fact, even though we think it's beautiful, there are biological reasons why you would want the sky not to be dark at night. Stuff lives at night, and they get distracted by our lights. Ever notice that bugs fly towards the lamp? Not supposed to do that. So, what are we looking at when we see this? So we see gas and dust. Okay, so this red stuff is dust, and it's red because dust likes to scatter blue light preferentially and send us their red light. And this stuff here, this gas and dust, is what we call interstellar medium. So this is the stuff between stellar, stars, medium stuff. Interstar stuff, interstellar medium. So this stuff is what makes new stars. When we think about the nebula collapsing, it is the interstellar medium collapsing into a nebula. Okay. All right, here's the galaxy that we live in. This is us. We are here. Okay. We are not that close to the center. We're kind of like more towards the edge. So if you're in Star Wars and they say, oh, you're on the outer rim, this is what they mean. The outer rim of the galaxy. Oh, Star Wars. Okay. And the whole disk is about 100,000 light years across. So light that is emitted over here takes 100,000 years to get over here, assuming that it's never stopped by anything. And of course, it's likely absorbed by something along the way. There's a big bulge in the center, and the bulge has a different color than the disk. What does that tell us? Different stuff, okay. It's not just different stuff, it's something very specific that you learned about in the homework.
Different stars.
Different stars, good. And what's different about the stars? Luminosities will be different. Something that I'm trying to hint at. They're more luminous, good. Age, which is old.
Isn't the blue stuff as well? Never mind.
I thought it started younger, so.
The blue stars younger or the yellow stars are younger?
Yellow stars are younger. The blue stars are
Okay, it seems like I just immediately grading his homework right away.
No, don't do that.
Okay, so which stars are younger? Blue. Why are blue stars younger? They burn faster because they burn brighter because they have higher luminosities.
Yes.
So blue stars are younger. And when I see a cluster of stars that's very blue, I know that it's new. Whereas I see a cluster of stars that's yellow, I know that it's old.
So
See how that works now?
So is it like the stuff got like expelled outwards and that's where it's creating new stars instead of the inside? Why is it?
Wait.
Yes, sir.
Let's make observations first and then we'll make hypotheses. We're just only looking at it sideways, or sorry, edge on, and then we'll look at it sideways and we'll see a different view. And we'll begin to learn more about the galaxy as a whole. Okay? We also have these things called globular clusters. These are just star groups, besties, right? And they're on vacation. They're not part of the disk. They go on these fun little orbits. Whee! Whee! With their besties. Okay? Okay. They form a halo. When you say, yeah.
So, do globular clusters have solar systems of their own, or is that only exclusively galaxies?
When you say solar system, you mean like a star with planets? So we think on average, every star has about one planet at a minimum.
There's no like minimum like there's not talking about average or there's stars without planets?
On average, we think that every star has about a planet,
So some stars don't have.
and some stars have 8 planets.
Yeah.
But if you take, say, 100,000 stars in the globular cluster over here, would you expect there to be planets?
Yeah.
Yeah, why?
So on average, there's what?
No, not just the information I told you.
It's the leftover stuff.
Right, so think about how we make planets in the first place. It's the leftover junk from making the star. Right? So if I'm gonna make 100,000 stars, you're gonna have a lot of leftover junk making hundreds of thousands of planets. Okay. Okay, so here are the primary features. You have the disk, bleh, bulge, brr, halo, and globular clusters, which are inside the halo. Okay. Sometimes you'll have like galaxies being friends. So this is ours. This is the Milky Way. That's us. So we don't have a friend. But like there is the Large and Small Magellanic Clouds is 2 galaxies that are kind of orbiting each other. One of them is very small. It's going around the other. Okay. Is this a real picture?
No.
I can't tell if Kobe was serious. Why is this not a real picture?
Probably was.
Well, he was smiling when he did it, so I couldn't tell. It's too far. What do you mean it's too far?
Too far from
The rest, you know, that basket in order to get from it back to the.
So you say we have to wait 10,000, 100,000 years in order to get the light out?
And travel that far, you wouldn't speed of light.
Okay, so the reason that I can't see this is because light can't travel that far, or that
No, I can't.
we haven't sent anything. Right? How long? What's the farthest thing we've sent? Yeah, how far away is it? Farther than Pluto for sure. So on this scale, how big is? If I use my fingies,
If you use a little, like a little, yeah.
like this big?
Oh,
Smaller. Smaller? Is my finger too big?
Yeah.
Yes, by a lot, right? By huge amounts. Okay, so we can only infer what it looks like from the outside because of 2 things. One, because we know where all the stars are. So we can construct what we call a 3D model. And then we can see other disk galaxies. And we can imagine what they would look like from an edge. They look at us, we look at them, right? That's another song too. I wasn't gonna do it. All right. So this is what it would look like from above.
I did
Yeah.
So I've quite a great question, but how big is Sagittarius A star, the black hole center of our galaxy?
Sure. It's not a star, right? It's a black hole. So we'll talk about it when we talk about all the stars that we do see going around it, and those help us to weigh. So here, what we're looking at is we're looking at a picture. This is a real picture, right?
Of course.
No.
For the same reasons that we just talked about. What else is wrong with this picture?
A label.
I feel like our
I mean,
swirlies are not that swirly.
Well, because when we take pictures of them, it would be labeled.
Yes, those are added after the fact, but yes, thank you for your point.
Our swirlies are not that swirly.
Our swirlies are not that swirly. So let's look at a real image of the galaxy. Okay.
UFO.
UFO?
This is the Whirlpool galaxy. And what's happening here is very similar to this picture that we just saw. Let's go back 1 step here. Okay, we had these different colors. What did I say about blue?
The newer stars.
Newer stars. What's red? So interestingly enough, in this picture of a galaxy, that's not the case. We have to take 1 more step backwards. What did we say red was when we're looking at a galaxy?
Wait, what?
Let's go back.
Yeah.
Yeah. Why is this red?
It's not
In the southern medium.
Yeah. Dusty gas is red. That's the interstellar medium that we talked about. The left of it. Right? So I see blue stars in here, I see white stars in here. Do I see red stars? You don't really see red stars for two reasons. One, they're not very bright. Okay? And two, they're gonna get obscured by all that stuff. What you do see is you see bright stars, blue stars, through a red filter. So you might see in these pictures a lot of gas and dust making things look red, but it's not a red star. It's really important to remember that. Okay. Let's go back to this picture. Here I have blue. What does the blue mean? New. What does the red mean? Dust. Okay. Yellow means old. Okay, there you go. All right. So here's the real picture. So now you're seeing this a little bit better, right? Okay, let's see if I can find all these things. You see the blue?
Yeah.
Good. Blue, right? Where's the red? It's in the spiral arms, okay? And I see white. Like white, yellow. So there's more yellow in here. And out here, in this like region, it also looks like dark, right? That's interesting. That's relax, please. Okay. So in these regions here, you have these little dots. And these dots have really bright parts in them. These are brand new star forming regions. So what do you need for brand new star forming regions? Well, you got to start with gas that can then collapse and turn into a star. Right? So you make all these stars and then you leave them alone, the blue stuff. You blow away the gas that's left over. We saw that in those beautiful pictures of nebula, right? Okay. As you mentioned earlier, this is the idea of spiral arms. How many arms are there? So is this picture correct? Too many swirlies. There's only 2 swirlies per galaxy. So next time that you're feeling like you want to draw a galaxy like this, don't do it. Okay, we're not going to do that anymore, right? Okay. So we see that there's not a lot of star formation in the halo. There's plenty of formation of stars in the disk. That's the blue part. Why does the ongoing star formation lead to a blue-white appearance? Is it A, because there aren't any red or yellow stars? B, short-lived blue stars outshine the others? C, gas in the disk scatters blue light? Show me your hand when you're ready. Let's vote on 3, 2, 1. Yeah, I got almost everyone. Someone want to explain it?
Well, if there's a lot more blue and white, that kind of means that in general, it's pretty young, right?
Yes.
So it has to live long enough to create.
Okay, so here's an interesting thing we got to think about. Are older stars made at the same time as young stars?
Yeah.
Yeah, it has to be, right, in order to get old. So that means I have red stars and I have blue stars. And I have yellow stars and I have white stars. Why do I only see the blue stars?
They burn bright,
They're brighter.
so they're more luminous.
They burn bright, so they're more luminous. So the light that I'm getting is mostly blue. And then as the blue stars die, the next most luminous star is the light that I'm getting, right? So they're all still there, and I can see them if I switch, right? Or if I can separate the light into its colors. So I can remove the blue, then I would see all the yellow and I'd see all the white. And then if I remove that, then I would see the red. In fact, the majority of the stars in the universe are red by mass. There's very few big blue stars, mostly because they explode quite quickly. It's easy to make little baby stars. Okay. That make sense? Okay.
What was right in?
You tell me.
Gas,
What was that?
a gas in the distance.
Is that right?
Blue outshines
Or-
yellow.
yeah.
Blue outshines others. Others being yellow and white. Okay. So if the cluster is young, you probably have some nice bright blue stars. There's no reason why we don't make blue stars when we're making stars. They just explode quick. Okay. This one is true, but it's not the reason why it looks blue-white. This is maybe true in some places, I just don't know where. Okay, so how do they all go? They all go like this. So this is a diagram, obviously. Interestingly enough, in the spiral arms, you think of them as kind of in this thin disk, but the individual orbits of stars at any moment can be going up and down out of the plane. And similarly, these halo stars, these globular clusters, they can be traveling on whatever orbital trajectory you want. Does this remind you of anything? Comets, yeah. So they act a lot like comets. They're going out of the plane, they're going in whatever direction they want. As they cross the plane, is there any danger of them smashing into another star? No, because space big. Space so big, no star will ever hit another star. And think about that for 1 second. No star will ever hit another star. We are going to collide with the Andromeda Galaxy. One of the galaxies will smash into. As that happens, hundreds of billions of stars will pass by each other. And the whole systems will pass through one another. And then they'll pass through one another again. And then they'll form into this big clumpy group. And in that process, we will crash no star into any other star. Nope. Nope. Mathematical impossibility. Yeah.
Would that same apply for like planets? Like, or they won't hit each other?
Yeah, planets, well, planets won't hit each other from just one planetary system hitting another planetary system. When we shake up a planetary system, comets and everything else, which are very abundant in a closed space, will certainly hit the planet. Ejecting one planet and having it come in from another place, that's a possibility. But two stars will not just collide into one. Because the average distance between stars is really, really large. Yes, but remember when we think about the words probability, right? There is a low probability that an atom will spontaneously become a different atom. That the probability is so low that it's longer than the age of the universe. So if you think about, you have some probability of the star hitting another star, and you run the simulation, you look, did they hit each other? No. Yeah.
They only collide if they're binary pairs that form near each other, that they eventually.
Those still are not a collision. So I can have two stars that form near one another. And they might trade mass. One of them might siphon off mass from the other, like we saw in order to build those supernovas at the end of last class. That's not considered a collision because they still have a mutual orbit, right? And they're going around each other like this. And while one might be sapping off the energy, that's going to change the orbit, but they won't crash into each other. Think about it in the context of angular momentum. If you have two objects, they're coming in like this, they're going to smash into each other. As they get close, they're pulling on each other. You'd think, oh, they're going to just zap. But they're coming in maybe at an angle with respect to a reference point. They got to conserve the angular momentum. So they're going to actually do that and fly out. Makes sense. Yeah, there's a lot of math that can show that this won't happen. No smush. Lots of hit inside of the planetary system. So when Andromeda comes by, it's going to shake. It's going to cause a lot of star formation. Right, all the gas is just sitting around doing nothing. It's suddenly going to smash into other gas, and that will certainly cause huge amounts of star formation. But those individual stars won't then smash into other stars. It's counterintuitive, but it kind of makes sense.
Would comets, like with that kind of orbit, also with Andromeda, would comets hit each other at that point?
In a single system?
If Andromeda and Milky Way, like when they combine.
Yeah.
Like,
So remember the scales are really important here, right?
yeah.
So like an entire solar system doesn't even fit into a pixel here, right? And all of the comets, thousands or millions of comets that might exist in the Oort cloud, you've got to really think about that as existing. Remember we made this analogy of taking the sun and shrinking it down to the size of a grapefruit, right? And so where was the edge of that solar system? Where was Pluto in that scale?
Outside the door.
Outside the door. But if I put the sun here, is it on campus? Is it in California? Is it in this room? What's that?
It was in Montana.
From here to Pluto?
Compared to Pluto, yeah. Pluto was what? Too far now. Nope, that's way too far. So the star itself, the next star itself is in New York. So that's a good memory, but of the wrong thing.
Wasn't it like the garage?
The what?
Wasn't that the parking lot, like outside the arena?
Yeah, so many of the planets are in the parking lot, and Pluto is at the observatory. Okay, so most of what we consider the solar system fits on campus. Right? And so you keep going, you would get almost all of your comets probably before you get to Joshua Tree. Okay, now think about that scale for a moment. All of our solar system is contained in a much smaller area than how much space we have to the next star. Because I have to now go across the entire US, as you said, to get to New York, where there's a comparably sized object. Maybe it has planets, maybe it has its own Oort cloud. So will the comets from one intersect with the comets of the other? No, very unlikely that they'll crash into each other. But will me moving by one of them with massive star cause something like the late heavy bombardment to occur again? Yes, absolutely. Right? Because that's a gravitational added distance push. Right? So our comets would come in and do some devastation to us. Cool. Okay. The bulge stars, the yellow paths. I have this as red. Does anyone see this as red? You see purple?
Oh, sorry, yellow? Are you talking about the line?
Oh, the lines, yeah. I was like, oh, I don't see that at all. And then I said green, but I think there's a better word for that. I don't know what it is.
Teal?
Turquoise.
Cyan?
Okay, I'm gonna use teal.
Cyan.
I don't even know what that means.
It's-
Okay.
It's that color.
You guys go.
Yeah, that's it.
Alright.
It's a main printing code.
Okay. So anywho, so these are the green paths or the halo paths. They have random orientations. Whereas we do notice that for the yellow paths, they're all basically going ring around the rosy, basically in a merry-go-round, right? In the same disk direction. We don't have stellar groups that are going backwards, right? They're going in the direction of the swirl. Okay. And oh my god, I hate that it's there. This says the word sun's orbital motion.
Because there's a chat for you.
Oh, do I have to open the chat? That's what Trinity has to say. She says, I hate you all. No. It says I can hear. Okay.
Did you say hi?
Not yet, no. I don't know if she can hear and she doesn't want to say anything. Okay. So it's important to remember that there's a bunch of mass in this thing. The galaxy itself has mass, right? That's not surprising to folks. However, we can do some fun physics. So we've talked about color and everything else, and it hasn't felt very physicsy. But we can remember that if I'm going around in a circle, then I'm going to have something like a circular velocity, right? So you could say mv squared over r. That is the circular force, centripetal force. And you can balance it with the force of gravity, as though all of this mass was concentrated boop, right in the center, like we were orbiting a star. Okay? So if we know how far away we are from the center, and we know how long it takes to go around, we can measure the mass interior to our orbit. This is a technique that we use for measure the Earth. This is the technique that we use to measure, say, Jupiter. Look at its satellites going around it and figure out how massive it is, right? We can look at Jupiter going around the sun. We can weigh the sun. Okay? So this is the process of weighing each of these objects. And it turns out we look interior to our orbit, and there's about 10 to the 11 times the mass of the sun. How many is this number? Big number. Bigger than a billion?
Yes.
It has to be, right? 10 to the 9 is a billion. 10 to the 10 is 10 billion. 10 to the 11 is 100 billion masses of sun. So when I say something as flippantly as there's 200 million stars, this is roughly what I mean. And you say, there's probably about as much mass here as there is there, or magnitude, right? Okay. That makes sense? Okay. She says, yes, I can actually hear you. Don't say I hate everyone, because I don't. That's correct. Okay. So the orbital speed and radius tells us about the mass. Okay. Oops, now I have to actually fix this though. Okay. Why do spiral arms develop? This is now not going to work, is it? I should never have clicked. Okay. Spiral arms are waves of stellar formation. And I can show you that this is happening. So here you have this like brown stuff, this interplanetary medium. As it gets compressed, it forms these blue stars. And then there's these spiral density waves that are going out. What's happening is you can think of them as, when we made this analogy in the solar system, we said that there's a disk of material, and that disk of material doesn't really pull it flat. That's not really the case here. Now the scales are big enough, the distances are large enough that gravity does become very important in squishing and pulling. The masses are high enough that gravity becomes important in pulling this together. And so what you'll see is whenever there's an over density, stuff get pulled together, it'll pull other stuff near it. And in a rotating system, this creates these very typical spiral patterns. Okay. Gas gets squeezed as they move into the spiral arms. Then this triggers star formation, and the young stars actually move out of the spiral arm. That kind of cool? Ooh, questions? No. Okay, so how do you form a galaxy? You start with a bunch of gas. Okay, just like our nebula, you can imagine that you start with a bunch of gas. This would be intergalactic gas. Okay, and you let it collapse. Okay, so you start forming this giant cloud. The scales here are immense, from hundreds of thousands of light years across. And out here at the edge, you might be forming your first halo stars. Okay, and then it settles into a disk, and these halo stars are going around every which way they want. And then you start to form your debris arms, and you get these spiral arms that grow into two tight pieces. Okay. So here's the question. Over time, gas in the galaxy is slowly getting trapped in long-lived low-mass stars. B becomes enriched from heavy metals created in the deaths of stars. C gets recycled as it works through the life cycles of stars, or D, all of them. Ready to vote? 3, 2, 1. Okay, why don't you turn to your neighbor and ask them what should happen?
Why?
Why?
It is.
That's not even all of them. They're all like, yeah, maybe definitely all of those.
Yeah.
Okay, I changed my mind. That's but kind of like. I had a moment where I forgot how to spell teacher, and I wrote T-E-A-T-U-R-E. That's how you should you spell. It's like they will go away so
Okay, folks, you ready? Let's vote again. 3, 2, 1. Okay, so we got a group of 4s, we got a lot of 3s and a couple 2s. No one liked 1.
Yeah. Is it a 4?
Is 1 wrong?
Yeah.
What does 1 say? What does 1 mean? People understand it?
In my head, it kind of means that you can't really go in.
Okay,
Yeah.
so let's say I have a red star. Red stars are small. And red stars live a long time, right? So once I form a red star, what does it do with its mass? There you go. What if its lifetime is longer than 13 billion years? Very good. So does mass slowly get trapped in long-lived low-mass stars? Yeah, it definitely does. It's a cascade, right? Certainly you build these large ones, but they explode and they give it right back. So that would be this one too, no? Okay, well, what about this one? This one seems wrong, right?
Both of them are right.
Process of elimination. Let's make sure we understand this. What does this mean? It becomes enriched from gas, from heavy elements created the death of metal stars. Okay, metals are increasing. We talked about metals. We said anything on hydrogen and helium. Is that true in the death of stars? Yeah, it has to be true. Remember, that's how we get gold. That's how we get plutonium. That's how we get silicon. Gold, yeah. Okay, I don't have any gold on, but so this is also true. So of course the answer is okay, let's keep using those brains. We're going to talk about star formation and lifetimes really quickly. Let's make a new friend. Don't work with people you've already worked with. 1, 2. Actually, here's what I'll do. I'll force you guys. There you go. Now you have to work with new people. Now you have to all find people to work with.
That's not fair.
That's fair. I think it is. You might have to make a group of 3. Sorry, Trinity. Oh, you got to send her good vibes. She says she's crying. She can't do this with us.
Oh, no.
We miss her. It's okay.
Everyone says they miss you. Lucia said you're not missing out, which is a lie. It's great.
Got one?
What?
Got one?
Yeah, it's my cousin.
Oh, I see. You're an increase of 2 or?
You can do it at the same time. Again. You know, Adam's family.
Not spooky enough.
Yeah. Isn't there a person that's older than Adam's family?
Probably many, yeah. Bald is
Oh,
spooky.
There
There you go. I'll be Uncle Fester. That's perfect. I won't hurt myself. Oh.
Okay. That's. Clarence Wiles and
Yeah. Yeah, yeah. No, so you don't get enough pressure and temperature. Yeah. Unless you're trying to write the sine wave, that's.
Oh, I've never seen this one.
This one?
Yeah.
Been there.
Yeah.
8 years.
You're old.
I'm old. Oh my god.
We're great.
Oh my god.
Okay, big.
It answers the question in the next sentence. Yeah. That you actually might. Find out.
Oh my god. Well, see, it's good. I look like I write love letters every day.
Yeah.
I can roll words. No.
It was gonna be
done?
Yeah, you got it. There you go.
I love his love letters though. In 13 billion years.
I told him, I was like, yo, you look like you write love letters in like World War One.
I'm asked for low, let's talk. Oh my god.
No,
Oh,
have
well,
you seen dinner?
He looks at me like I'm stupid.
Right.
Oh.
Secret.
So star A is smaller than star.
It's 6 times the math. And figure started very hot.
Yeah.
One
One
that's.
that's.
What's that? No, it's not. Protostar means not yet a star, and we define star as nope, nope,
That's planet.
nope, fusing.
He said it like 8 times. I'm so sorry.
He's got you're speaking very loud over him. I gotta listen good.
So that's.
More than 6.
That's. So one. Six.
Yeah.
Or like, yeah. No, one. So you can just like, what's this? Can I like, right there?
I'm sending the board.
I don't put degrees and I was like.
I just put 4 zeros.
Yeah.
That's what I heard.
I don't, right?
I don't know. It's hard to tell though. I mean, that could be affected by the fire, changing the, whenever there's particulate in the air, it can change the ability for us to predict what the weather will be like. Because it changes the local thermal conditions. So I'm hoping that it'll push away, anything that's coming, but if it's one of those fronts, right, then we're fine. Is it really? Is it another river? Oh, geez. I mean, you can have a low pressure system that'll do that too, but it would be annoying if that was bringing up more rain. I mean, I guess rain's good, but
I think rain's predicted for Monday for exchange.
all done?
I guess.
I don't know, you tell me.
If I wrote.
Age and mass are not proportional?
Like,
They just always writing you say it.
you know what, it's like a wrong order, the sense of structure is off. Okay, last question.
Is that concept? Star A, okay, star B 6 times the mass of the sun. So it's probably, yeah. Cause star A.
So which one is bigger?
So,
Star A. Star B. Star
B is bigger. So B is bigger.
So then it'll burn through its fuel faster. Because it's nuclear. Yeah.
Yeah, what's the rate?
a star with twice the mass, you have a fusion rate that is. Yeah.
Think about the HR diagram for a second.
Not.
Right.
Okay, here's the HR diagram.
I have.
And across it is the main sequence.
Yeah.
And this stuff up here was bigger than the stuff down here, right? This is bluer, this is yellow. which direction does lifetime go?
Like, what do you mean, like long,
Like-
long
like
living?
this way,
Okay,
yeah.
so luminosity went,
So
lifetime,
finds
right.
enterprise mass versus solar mass.
I remember reading 10 to the 7th, 10 to the 8th, 10 to the
Okay, so it's changed by what factor?
10.
10.
Yeah, so log-
The logarithmic. And how is the mass changing?
It's like.
Kind of linearly, right?
Yeah.
So they would, you're right, that you said that they're not linear.
And then.
They're not linear. What's the relationship?
Logarithmic.
Logarithmic by a factor of 10.
So we could just put, instead of linear, so we just say logarithmic.
So your answer is correct. But I'm saying the way that you reasoned it, right? You think of it through the HR diagram.
Oh, okay,
Because
so
it's
through the HR diagram, we
You
could
could
say,
say either way, right? As long as you're thinking through it. Remember that you don't have right answers, the way for you to like.
okay, so. I change that, I change that, so.
No, we just talked about it, I get it. Exponential increase in rate of fusion, yeah. A few more minutes and then. I'm gonna do, there's one that we did over the summer, which is you fill up balloons, and then the color of the balloon is the color of the stars, and you make the local neighborhoods. I think actually Lucia was there for that, right? Didn't we do the local neighborhood with balloons? Were you in that room?
I was at the observatory when that happened.
Okay,
Yeah, we were trying to.
maybe Isabel. but she's
I was
gone now.
like screaming at children, not children, I was screaming at people that were slightly intoxicated
Yeah,
the
that's right.
entire time, and they started raging, and I was like.
Okay, folks, let's find a good breaking point. Are we good here? Are you on page 2?
Yeah.
We can finish this also. You have one more or two more? Do two more. Do two more really quick. Grab your water, grab your snackies. Done? Grades done? Sure. Yeah.
Because not A is.
Oh, yeah.
You're not being.
Okay.
Sorry, okay. Are you okay? Get her.
Ready?
Oh, sorry. I didn't see that one.
Okay, so we were talking about different parts of the galaxy, and we can see halo stars forming in other galaxies. Cesar! Cesar! He dropped flies. Thank you.
Why? Why?
Because I don't want the ones in the front.
Uh-huh.
They're connected to the ones in the left. Sorry. This is the way it is. Things will never be the same. Okay, so what you're seeing here is detailed studies show that, you know, we can do these simulations. Basically, you do something that's called a smooth particle hydrodynamic code, and you treat it like a fluid, and it collapses under the influence of gravitation. And if you really like gas dynamics or galactic dynamics, you'll find that fluids are actually directly connected to these. So if you like computer simulations with fluid flow, they have a deep and important connection with gravitational dynamics. Oops, down to me, speed. Okay. So if we look at the center of the galaxy, we'll see Well, because she's in my fluids class, so she doesn't want more fluids talk in another class. So if we look at the center of the galaxy, as you just mentioned, there is a funny thing going on. It's very haha funny, and not unusual funny. So as we look, we can zoom, pinch to zoom, but we have to do this with different spacecraft. Okay, sometimes they're spacecraft, sometimes they're telescopes, sometimes they're observatories on Earth. And we can use very large radio observatories, or we could use infrared spectrometers. So this is what it looks like in the visible on the left-hand side. And notice the scale here, 200 light years. So much, much bigger than, say, our solar system. If we zoom into the same picture here, we get this on the scale of 50 light years. And there's clearly something happening here. Yeah, we zoomed into this area right here. Maybe I'll draw a little thing next time, like a little box. But this piece here is this piece here. Now, the only thing that happened is I changed wavelengths. This is in the infrared. Okay. And I can zoom in again. Okay. So I move that picture to the left, and now I'm looking at radio emission. So have you ever seen Arecibo? Okay. Okay. You ever seen Arecibo in contact?
No.
Arecibo, the telescope?
No.
Big dish in the ground. No one's seen contact?
Oh,
Yeah. Okay, so when we see radio observations, when you see these radio telescopes, for example, you see these large arrays. Like, do you remember when she's like in contact, she's like trying to get the information, and there's these big looking telescopes behind them? Yeah. Have you ever wondered, that doesn't really look like a telescope like I think it looks like, because there's no eyepiece or anything like that? Because it takes in radio waves. Radio waves long. So you need a big collecting area to concentrate them into a point. And that's the thing in the front. So when you use your TV, that also collects radio waves, but not from space. Yeah, little tiny baby that. And so this is what it looks like when we zoom in to this region here. Okay. There's also clearly something going on. Okay. And there's these little concentrations that are very hot. Let's zoom in again. That's 1 light year. Okay. So we zoom in here, we see there's tons of stars. There's a bunch of these. The reason that it's all hot in the left-hand side of this image, these are all stars. They're close to each other, so I can't tell the difference between them yet. But as they get closer, I can individually start to pick them out. Notice this is in the center of our galaxy, right? Like 50,000 light years away. Okay. So I'm looking closer. Let's zoom into that point. Okay. So this is in 1995. And this is a video where we can individually identify stars and name them. So they have these really beautiful, wonderful, intriguing names like SO1 and SO2. And over here you have SO49 and SO19. I wonder how these were named. Yeah, exactly right. You can kind of tell, look, this one's brighter than this one. They found this one first, they found this one second. SO1, SO2, and then the ones down here, 45, these are the dimmer ones. They're harder to find. Right? Well, I'll tell you, you'd love to do that. I'd love to do that. But what's the problem?
We have to find them all and then make the picture.
No, actually, they're moving. So let's play this right now, and you will see that all of these stars are going to move. Okay? Come on now. Oh. Media not found. I will find that and I'll put that in Monday's. They move. So this is 1995.5. So it's like halfway through the year. And the simulation, not the simulation, the observations show like repeated measurements of the center of our galaxy. And then we can see that they're moving around something that isn't there, that isn't bright. So in fact, we watch these stars, right? And we see that they're all basically moving around something in here that we can't see. There's no brightness. So these are the bright stars, bright star, bright star, bright star. They're moving around something that isn't bright. What? Radical? Black holical. That was David's line, but he didn't want to get in. Yes, there's a black hole in the center of our galaxy. And notice the scale length here. This is now an AU. So if I take that distance and I take 1/10 of it and I say that's about 1/10 of an AU. Okay, or sorry, 1/10 of this, which is 160 AU. How big is 160 AU? The scale? Right, and what was Pluto's orbit? 40, 50, yeah. So that's about 3 times larger than Pluto's orbit. That's still well within the Oort cloud. Right? It's well within the Kuiper belt. So our entire solar system can fit like right here. Is that crazy? And then right in here, something is being orbited. We said that black holes don't suck. They don't just grab stuff in and never let it go. You can orbit a black hole very successfully. And in fact, all of these stars are. And we see them moving on timescales that are human. Right? So we can see over the course of 20 years, stars moving in and around these objects. We see the same star slingshotting around this invisible object. Yeah.
Do you know how fast the fastest one is going?
It depends on the time. Like here it's moving very fast, and here it's moving slow. Right? Yeah. Oh, I'm sure, yeah. I think this is from Pearson Education Group, so I don't think they're as proud as like say the original scientist who made this picture. Anyhow, so that invisible thing is about 4 million times the mass of the sun. Cool? Not cool? Super cool. Let's use some numbers. Let's remember how much mass was interior to us. We are orbiting around in the galaxy. How much mass was interior to us?
10 to the 11.
10 to the 11, which was about
100 billion.
100 billion. Significant or not significant? No. Is this the reason why everything is orbiting around? No. So some people have this conception, they hear these numbers, they think about these numbers, 4 million and the sun. Wow, that's massive. But really, there are just millions and billions of stars that are also hanging around that are causing everything to orbit in the same direction. Okay, it's not like this has some special power over the universe. Okay. Okay. Sometimes we see X-ray flares. And these X-ray flares are what happens when stars get too close. Now I said stars don't suck. Sorry, black holes don't suck, but stars aren't like solid objects. And just like when a comet gets too close to the sun, it can start to burn up and break apart. Stars can do that too. So as the star gets close, it feels a tidal force. It gets pulled differentially, and that material then falls in to the black hole and creates X-ray flares. So you see these enormous X-ray flares coming off of Sagittarius A, which is the name of our black hole. And so you say that it is an active galactic nuclei. The stuff is falling in and making it bright. So people who study active galactic nuclei, Dr. Hood. Oh, cool. Way to tie those things. Okay. Okay, then let's talk about the Hubble Deep Field really quickly. And this was true up until like last year. So I'll update these slides for Monday. We'll look at the JWST deep fields. Telescope time is hard to get. Lots of people want to look at stuff. And someone said, look, I want 90 hours of looking at the same part of the sky where there's nothing there. And we're like, that's stupid. Why would you do that? There's nothing there. And he says, I just want to do it. Okay, just let me do it. And finally, they let them do it. Okay. And what they found was in this dark part of the sky, see this piece here? It's tiny, tiny. Let me get out of the way. See this tiny, tiny pixel here? We zoom in times 50 to get this. We zoom in times 30 to get this. And it looks like nothing's there, right? But every single one of these, except for that and that and that, is a galaxy. Every single one. There's no stars in this image except for that one, and that one. And I can tell that they're stars because they're shiny. They have a crossbar. That crossbar is from the telescope's crossbar. These here are galaxies. Every single one is a galaxy. And I can already see cool stuff, right? What's that? Spiral galaxy, good. What's that? Spiral galaxy, what's that? Maybe, I don't know, it's hard to say. Okay.
So what would they want to just like do images with like how you said 90 hours? How can they do weeks on it? Because it takes too long.
Because other people want to do other stuff.
People are
I know, right? It's
Instead
so
of
rude.
and then
It's so rude. Okay, so let's.
over like Christmas time. Look, it's working.
No, the telescope's continuously running. It's always taking observations. You basically submit to a stack, and your submission goes to the bottom of the stack, and they take off the top of the stack, electronics, of course. And they point to one direction for a certain amount of time, and then they send you the data. And then you go to the next one, right? And this stack is always in operation. Okay? Because it's $1 billion spacecraft. So if it's ever not working for any period of time, it's a waste of money. Okay, so this is the Hubble Deep Field, and we'll talk about this when we talk about cosmology, the idea of the galaxy's age, or the distance in the universe. We've kind of touched on this a little bit already, but in this process, we can see some really interesting phenomenon already. So you have different types of galaxies here, right? If I'm just looking at the spiral galaxies, what colors do I see?
yellow.
Where?
Bottom right.
Here and
Oh, the right.
here.
Yeah.
Good. So I got some yellow. What else do we got? Blue right here.
Right.
Maybe here, maybe, right?
Yeah.
So what do I know about this galaxy compared to this galaxy?
That was older, younger. Yellow. Yeah.
Yellow's older, right? You can see the age of galaxies in here. What about this stuff? Is it a star?
No.
It's a galaxy, but it looks different.
This part.
So now in this picture, I can see many different types of galaxies. So now I'll need to describe what I'm seeing. So we took for granted that we look like this. But I see this all of a sudden, and I'm like, well, that can't be a star. It has to be something new. And also like that kind of looks spirally, but like that kind of doesn't.
It's a little messy.
It's a little messy. So we got some like messy boys in here, and like, what is that? Are you drunk? Get it together, right? And some of them are flat. Is that a problem? Like this flat piece? No, that can just be on its side. That one's okay. Okay, so circle balls, discs, and messy boys. Okay, so now we have to understand and explain them all. And here they are. Circle boys, messy boys, spiral boys. This is like a generic term. So this could be like messy boys, spiral days, and circle girls. Is that
Okay,
better?
thank you.
Just so we don't exclude everyone. Okay. All right, so how do we get there? These are all part of the same classification scheme, and we'll make this classification scheme if we get weather. Essentially what it means is if you look on the right-hand side, we think that this is probably the way that they evolve, and we see this from the color. So for example, spiral arm galaxies tend to be very blue. There are some exceptions to this rule where we see older spiral galaxies. But for the most part, when we see elliptical galaxies, E, then the elliptical galaxies tend to be quite old. We don't see blue spiral galaxies. Similarly, we see spiral C, B, and A types, how tight their spirals are versus how loose they are. Okay? They also may have a little bar in the middle. So in these ones up here, it's a central dot. And here there's a sort of separated bar. So these are called spiral bars, and these are called spirals. And now you know all of the galaxy types. Notice that spiral bars end up being more circular, and spirals tend to have a little bit of a bit to them. And then they go and they become short, and then they become circular.
Wow.
Right? Okay, scientific terms. We tend to find spiral galaxies together in groups of galaxies. So we'll see like a spiral galaxy forming near its friends. So you see these three probably are all together. And then this one in the background might be in the background. There's some other things here. Do I see stars in this image? No, everyone is a. Just fucking mind-boggling. Please keep in mind how dumb that is. There are no stars in this image, only galaxies.
Well,
Yeah.
why don't you believe
The whole galaxy.
Yeah, so we'll do that a different way. We will use the fact that the light is deflected by mass, and we will measure galaxies that way. Does that make sense?
Yeah.
We'll use a lot of different metrics. It's kind of hard to tell. That the curving of space will give us some metrics. We're gonna use some other things about how far away they are and how bright they are. Then we're gonna infer how many stars there are because that's the only thing that can be making light. But it'll require us to understand many more tools that we'll get to. Okay. All right. Elliptical galaxies are much more common in huge clusters. So we see all of these little tight together. And in fact, here we begin to see what I told you about. These like curved pieces, you'll start to see some what's called gravitational lensing. You'll see some bending of the galaxies in the background.
Wait, that's because of the like central cluster, right?
Yeah, right in the middle. So this is bending of galaxies in the background.
So does that mean that like the cluster is somehow farther than it is shown in the picture? The lens?
The cluster is in the foreground.
Oh, so that kind of thing.
Yeah, so there are stars in our galaxy.
Oh, ow.
And then we're looking out of our galaxy at this cluster. That's the focus of this picture, and I think these are probably in that same cluster. And then in the background are these individual, see these ones here, all over the place? And then there's a teeny tiny bit of lensing going on.
Also on Yellowstone, it sounds like old cluster.
Yeah, very good point. They're very old clusters, and we tend to see that with the ellipticals. Ellipticals tend to be very old, and that's because they have gone through the dynamical history of being flat and getting squished into a circle ball. Yeah, a circle girl. Okay. So, what are spiral arms due to? The rotation of the galaxy winding up the stars in gas, a density wave that causes gas to clump up together like cars in a traffic jam, the supermassive black hole in the center of the galaxy slowly sucking in all the gas in the galaxy. That was a good one. High pitch, but all right. We ready to vote? Or is that too distracting? Let's vote on 3, 2, 1. Okay, so what do we think? Let's do some arguments here. Is it this one?
No,
Why not?
black holes don't.
Black holes don't suck.
They're awesome.
No. The corollary is not true. Therefore, okay, so the remember when we said that the mass of the black hole was 4 million M suns? Small compared to the 100 billion that is the interior mass of the galaxy. The mass of the galaxy as a whole is probably closer to 200 billion, right? So this is small and negligible. It's not giving you the structure of the galaxy. So that is a coin flip, right? So which one is it?
A.
You like A. Why?
It's quite fun.
It's a coin flip. No, that's incorrect. That's not the way we reason through these problems. Yeah.
I like B,
Why do you like B?
because the density wave kind of explains how, like, in the very center of the galaxy, the black hole will keep in orbit the nearby stars. But then if you kind of take the average density of that area, though that mass causes the nearby stars to orbit that one, and then it just kind of keeps piling up until you get to the edges.
Okay,
I thought there
I like
were-
this idea, but we have to tweak it slightly.
I thought there were no traffic jams in space. Space big.
Space big, but remember, traffic jams don't necessarily always involve hitting the car in front of them.
Oh,
saying we
the
can't
space
use the
big.
car, but we
Space
have
big.
to.
Space big, but space doesn't mean you can't slow down because there's a car in front of you. So if there's a car in front of you and a car behind you, then I'm being pulled in both directions. I can be slowed down because there's two cars behind and ahead of me that are slowing me down.
Sorry.
So in fact, it is this one. Your idea is almost working, but we haven't, that doesn't yet describe why there's arms, right? Because that would just mean that we were all orbiting together. And the reason yours is right until we think about as we go out, let's say I'm going faster than someone else. I'm gonna start to run into them, but there are gonna be people piling up behind me, and that pile up is gonna cause star formation. Okay. Now you understand galaxies. That's as much as I like to do on galaxies. We can certainly do more. In general, we'll talk about how galaxies form, but we need to first understand cosmology. We have to understand how we even have a universe in the first place. So we're going to talk about something called distance measures and how the fuck do we know how big anything is. It's surprisingly complicated. What's the first step? And don't say guessing.
Measuring our own.
Measure what?
Our own.
Measure our own what?
It is defined measurement.
Yeah, we have to define a certain set of measurements, right? So we need to define how big we are. We need to define the distance between us and the moon. How do we know how far it is to the sun? That's a question.
How fast is light get here?
Okay, good question. So how would you do it to get, how would you, well, I want to know how far away the moon is, what I do. Reflect what light?
Laser.
Yeah, maybe shoot a laser on the moon. It's brilliant. Have we ever been to the moon?
Yeah.
Nah. What if we put a mirror on the moon and then we shot a laser there?
That'd be so cool.
That'd be so cool, and we did that. So on Monday, on Monday, we'll talk about all the distance measures, starting with both radar ranging and laser ranging. And we'll build up an understanding of how we know how big the universe is, and then we'll talk about cosmology and why it seems to be that way. Okay?
We take Astro 3000.
Any questions? Okay, thanks, folks.
Oh.
It's like my doctor.
Bye, Trinity. Deuces. What does deuces mean? I don't know if that means.